Thank you for all of you that are still here. We're slightly depleted. It always happens towards the end of the conference, I guess. I just wanted to take a few moments before the last talks to thank the team that have helped make this happen. So first of all, can I get the local organizing committee to come out front, please? You might not have been expecting that. While they're doing that, I want to thank the scientific committee for all their help in selecting such a great mix and balance of plenary speakers and the mini symposia. We had a huge number of mini symposia submissions, a lot of work in going through all those. And thanks especially to Suzanne Ditlevsen for coordinating all that. And she knows we exchanged quite a lot of emails over the last year or so. So yeah, the scientific committee, and then please thank you to the local organizing team who've been fantastic. So I want to say who you are first, because so we got Daniele Avitabile, who handled the posters really fantastically. John King, behind is Jonathan Wattis, Steve Coombs, Bindi Brook, who found Kellam Hall for us, and it was fantastic Wednesday night if you were there, and if you weren't, you should have been. Rudiger Toole, Etienne Farco, and Ruben O'Day, who've all been wonderful colleagues, and it's been a real pleasure to work with them over the last year, perhaps more than a year. Thanks very much, guys. Wow, this kind of feels harder than the opening bit for me. Can I get the blue t-shirts up now? Is that too much? I think we should get them all lined out, and somebody please, we must have a camera. Or use your phones, take pictures. It looks like such a lot of you. Wow. So we've never seen them all together in one place up to now. So this is the consequence of having so many parallel sessions. Yeah, we've got at least 1.5 times as many helpers as there are parallel sessions, and they have been outstanding in ways that you wouldn't believe, including going to accident and emergency last night. So please give them a big round of applause. They've been fantastic. Good guys. Right. Okay, and is Elizabeth here at all? Is Elizabeth Booth here? She's not here. Okay, we'll do that offline then. David Hawker. So David is our research facilitator, and he has coordinated all the work with the sponsors, including doing a lot of the heavy lifting, putting up the sponsors' stands. So we got a little something to show our appreciation for all your hard work. Thank you, David. And then finally, Daisy, are you here? I'm sorry that we had to twist your arm. If you'd like to come down, then I've got something for you as well. And thank you so much. And Santiago has got something too. So I would like, go on. Yeah, there's probably nothing more to say. I think everyone will have received emails and emailed Daisy about something, and she's been super helpful with everything, and it couldn't have happened without her. So, and on that note, we'll have one more round of applause, and I'll hand over to the chair for John Rinzel's talk. Thank you very much.
Okay, well, thank you, Marcus, for running such an amazing meeting. It's a great honor to be able to introduce our prize speaker, first prize speaker of the talks this afternoon. So on behalf of the Art Winfrey Prize Committee of SMB, which consisted of Jim Keener, Mike Mackey, and Anita Layton, it's my honor to present John Rinzel as the Winfrey Prize award winner. So the Winfrey Prize is to commemorate Art Winfrey, who is pictured here, who passed away far too young. He was a pioneer in the mathematical biology of pattern formation and of oscillatory dynamics, and the prize specifically says that it's to honor theoreticians whose research has inspired significant new biology. And the committee spent a great deal of time deliberating before settling unanimously on John Rinzel, whose work indeed fulfills that criterion. And the specific language on the plaque, which he received last year when he was unable to attend, was for developing dynamical models that have inspired new experiments and insights in neurobiology. John's work has spanned the whole range of neurobiology, and I think he's going to share that with us today in the context of something to do with cocktail parties. John?
How about that? You hear me? Is it too loud? No? Well, I'm deeply honored to get this award, particularly since it's in memory of Art Winfrey, who was an extraordinary scientist, generous, creative, had his own individual way of thinking about things. Art and I became friends in 1972, so we were taking parallel pathways on studying excitable systems, and he was doing, and also oscillations, he was doing biological clocks, and he was doing Belousov-Zhabotinsky reaction. And this is for you, Art, to witness that this Society of Mathematical Biology has accumulated so many people in a conference together with the ECMTB. We would not have imagined this 45 years ago, believe me. So it's great. Let me try to get to what we're going to talk about today. Okay, we can start my clock going now. Okay. So I'm not going to be talking about those excitable systems or that history. I'm going to be talking about something that my group has gotten involved in the last 5 years or so, and it is about auditory streaming and perceptual dynamics. And we're going to be focusing particularly on ambiguous scenes. So I'll tell you a little bit about ambiguous scenes, model systems that people study for vision and audition. We'll talk about models. These are basically competition models for the different streams or different percepts you're trying to resolve in an ambiguous world, and so on. And there was some previous stuff on what I'm talking about during this week, mini symposium on perceptual and cognitive dynamics on Wednesday. James Rankin is also here. He's a postdoc in my lab now. And Tony Gilliman also talked about these kind of perceptual dynamics. So in confronting a scene, there are ambiguities in the scene that we have to resolve. In vision, there are objects that are occluded, and you are trying to resolve what that could be, that partly visible object. Or in motion, you can imagine a car going past a stream of telephone poles patched very closely together, and you're catching glimpses, and you have to fill in dynamics and so on. So we're talking about resolving ambiguities. Of course, there's computer algorithms that do these kind of things, but we're interested in brain mechanisms. In the auditory case, in the case of audition, that segregation of objects is called auditory streaming. And the the problem is to identify the different cues of an auditory source. Is it pitch? Is it location? Is it loudness and timbre? You're putting all these cues together, and you're tracking it in time. It's a little different than vision, where you can, you can see the whole thing and go look at it again if it's a static image. But in audition, it comes, it's gone, it comes, it's gone. So it's a very dynamic situation. And a classical case is the cocktail party problem. One of the phenomena is that you walk into a party room and there's many voices and it sounds like gamish at first, and subconsciously you don't realize it, but your brain is separating out those different sources. And when you choose to focus your attention, you can pick up a conversation over there. So there's two aspects to it. There's the segregation at first, or streaming, and then there is your attention that you can devote to it to resolve it. So there's these different cues. Another kind of cue is timing. So here's an example of several different auditory sources: a clarinet, a hammer, and a person speaking. And this is the spectrogram of those different sounds as a function of time. But you can see that there's many different frequencies associated with some of these sources, but they are coming together. So that coincidence, that coherence, is another kind of cue. So there are these ambiguities, and the models we choose are strongly ambiguous, so we can try to get some sense about how a more realistic situation might deal with this. Daniel Presnitzer says our perceptual systems constantly operate in the inference regime in an ambiguous, but we're generally not aware of it because, fortunately, one highly plausible interpretation usually trumps all the others. But it is a process that's going on in your brain. Okay, so you're familiar with some of these visual scenes that are ambiguous: the faces vase image, the Necker cube, and you know that if you stare at them, your perception will alternate on the time scale of a few seconds. Well-studied experimental setup in visual psychophysics is Binocular Rivalry, where colored glasses are used to present one image to one eye and a different image to another eye. So here you see one eye viewing a grating going in one direction, a moving grating, and here a moving grating and the other eye going in a different direction. And instead of your brain merging these images, it segregates these images from the two eyes, and you perceive an alternation between left eye, right eye. So it's one of the first examples that people studied for perceptual rivalry. So here you see the percept red for the red grating and red for the red grating. So it's alternating, but it's not very periodic. It's stochastic, and the distribution of dominance times, or the distribution of percept durations, is typically gamma-like or log normal. And typically, the data that are analyzed show very little correlation from one percept duration to the next percept duration, almost as if they're independent from much of the data that's been looked at. So here's an example of a kind of stimulus we use in the lab for visual bistability. It's got two gratings, and these two gratings are at different angles, and they're drifting. So depending on the angle, if the angle is small between their normals, you'll tend to see coherence. But if the angle is large between the normals to those two gratings, they'll be sliding across one another. For intermediate angles, you will see this alternation between coherence and transparency. So it's a very quantifiable stimulus. You can change the angles, you can change the speed, the wavelength, and so on. So you're the subjects now. Stare at the dot. Is anybody experiencing more than one percept? Is anybody experiencing more than two percepts? So this is actually an example of tri-stability. If you look at the one that's sliding, it appears that one is on top of the other. So there's a bistability between a depth perception in this as well as coherence and transparency. So we're going to be talking about an auditory analog of this to understand segregation. So here is the dynamic plaids. And now we're going to be talking about interleaved sequences of two tones. So these are constant tones of certain frequencies, A, and B, B, B. Okay, they're interleaved in the form of triplets, ABA, blank, ABA, blank, ABA. And depending upon the tone frequency difference, you're going to have a different percept. So if the tone frequency difference is very large, you're going to be able to hear A, B, B, B simultaneously. But if the tone frequency difference is small, you'll hear them as galloping kind of rhythm is described as ABA, 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 ABA. So for intermediate tone differences, you will be seeing ambiguity. You'll hear bistability. So there's two parameters that we use in these studies, the tone frequency difference and the presentation rate. How much time from the beginning of one tone to the beginning of the next tone. So this is a small frequency difference. This is two semitones. 12 semitones make an octave, right? So this is a small frequency difference. Here is a large frequency difference. Most people can hear the two streams in this case. And here's an intermediate frequency difference. You have to listen to this for a while. Did anybody hear two percepts there? Okay. And if I asked you what was the first percept you heard, how many people would say it was galloping? Did most people experience galloping to start? Yeah. That's typical in many of these perceptual grouping phenomena. Like the plaids, first, if the angle is not too great, the first thing you see is integration, transparency, or coherence. Here, the first thing many people hear is galloping. So people can study these things in the brain in an indirect way through fMRI imaging. For binocular rivalry, it's been done. And for the faces vase percept, it's been done. In this case, you're doing MEG, and you tag the faces with a certain flicker frequency, 12 hertz, or you tag the vase with a different frequency difference, 15 hertz, and MEG can pick this out. And the subject is pushing a button to tell you what their percept is. Okay? So here, when the MEG is picking out the 12 hertz rhythm, activity in the brain, the subject is pushing vase. But when it's experiencing faces, it's picking up more like the 15 hertz rhythm. So this is one kind of way. You can also try to do electrophysiology by sticking an electrode into the monkey's visual brain while the monkey is perceiving binocular rivalry or whatever. And you can see alternation in activity in higher levels of visual cortex. Now, these experimentalists, the thing you don't normally get is the percept, right? How does the dog or the gerbil or somebody tell you what their percept? Well, they've trained the monkey to report their percept. So in this case, you have the percept together with the electrophysiology. Okay, so the conceptual model for this kind of business is very simple. It is, the simplest models are, there's some population of neurons somewhere that represent one percept, and some other population of neurons that represent the other percepts, and they compete with each other through mutual inhibition. Okay? So if one percept is dominant, it steps on the other one. And if there's a switch, the other one becomes dominant and steps on the first one. Okay? So we know that there's alternation. So somewhere there's a mechanism for alternation between one percept and the other percept. So usually you build into these models some kind of adaptation. Who's ever dominant maybe gets tired of firing or pretending driving inhibitory synapses, and there's a switch, so on and so forth. So that's the conceptual model of the simplest type. I call this a percept-based model. Okay? So mutual inhibition gives you exclusivity. Okay. Oh, yeah. So we heard about mutual inhibition in the talk on Tuesday morning by Leah Edelstein-Cachette. She was talking about cell shape and the molecules that were competing with one another to control the cell shape. Sometimes both could be active, but sometimes one was active or sometimes the other. And there was even oscillations in some of the cases. That was the rock and roll thing she was talking about. So this pops up everywhere. This conceptual model is the same kind of model that arises in simple forms of central pattern generators that we probably bit our teeth on when we first started hearing about neural oscillators for driving alternating muscle, antagonistic muscle groups. Okay, so the mathematical framework for this in a neural context is the so-called Wilson-Cowan model. Wilson-Cowan model is going to give us the dynamics for the firing rate of a population, okay, given its inputs. Okay? So we're not, in the neural sense, we're not following action potentials or spikes per se, but probability of firing or firing rate. So in this unit is getting input from its partner, which is inhibitory. It has some slow negative feedback process in it that I called adaptation. And it's getting some input that corresponds to that percept. Okay? So the equations look like this. There's a dynamical equation for the firing rate. Tau is the recruitment time constant for the activity in that population. Okay? So at steady state, if the input were constant, S is the input-output function of these neurons. Input goes up, firing rate goes up, saturates. There's a threshold for half firing rate. Okay? So at steady state, if this input were constant, the firing rate would be R1, according to that relationship. And the inputs to that system are the inhibition from the partner, the negative feedback adaptation with strength phi, and the perceptual input I1. Okay? A is this adaptation variable, and it's driven by the firing rate. Its adaptation tends to increase with firing rate, and it does it on a very slow time scale, tau A. So tau A is a slow process here. It's going to set the time scale for the alternations, for the fatiguing process that causes the switches. So the system is symmetric. Okay? Population 2 is also getting mutual inhibition, slow adaptation, and some input. Okay? So these models were, this general framework of firing rate model was Wilson-Cowan, 1972-74. It was put into this framework of competition for Binocular Rivalry by Lang and Chow in 2003. That's sort of been our starting point for these. As this talk goes on, I'm going to bring us toward a model that's more sensory-driven, not just percept-driven. We're going to be able to specify the sensory input. Is it this grading, this tone, that tone? Okay. Okay, so this is the half-center oscillator, so-called half-center oscillator that drives rhythmic muscle behavior. And it's interesting in this system, usually I tell students, if you've got neural excitability, if you've got neural oscillations, there's usually some fast autocatalytic process, regenerative process, and then some slow negative feedback process to restore the system toward rest. So in a network, the fast autocatalytic process would be recurrent excitation. In this system, there's no recurrent excitation yet. Okay, it's just pure, but there is a positive feedback loop because I'm stepping on somebody who's trying to step on me. So that's a minus times a minus is a plus. So there is positive feedback here on a fast time scale. Okay, so it's not hard to get this system to go into alternating activity patterns. Okay, this is in a sort of, there's a relaxation oscillator because the adaptation is very slow. So if you look inside of one of these units, it's up. Adaptation is slowly building. It gets to some critical level, and then there's a switch down. Adaptation recovers, and so on. Okay? So I think Leah may have even shown the phase plane for mutual inhibition for her antagonistic molecules. And here is the phase plane corresponding to mutual inhibition. This is the null-Klein for the R2, for the population 2. That is, as population 1's activity goes up, the population 2 activity goes down. Okay? And the null-Klein for the population 1. So they intersect in 1, 2, 3 places. That's an attractor for population 2, dominant. A lot of firing in population 2, nothing in population 1. This is population 1 dominant, okay? That's a saddle point. So if you start somewhere, you go to this as an attractor, or you go to this as an attractor. That is thinking of sort of a fast, slow analysis. I've frozen the slow variables to look at this picture. This is the fast dynamics. You go to one of those attractors, you sit there, and then things change, and you have to leave that and go somewhere else. Okay. So this is based, I'll take just a momentary sidetrack. This is the setup that is involved in decision-making models in the brain. People are now studying, by recording from monkeys' brains as they're doing tasks, where activity is showing up to indicate what the decision will be or what the decision is. And models of those decision processes say yes or no, and they're mutual inhibition, like this. Okay? So this was in a talk earlier this week in one of the contributed sessions by Kung-Fang Wang, who worked with Xiaojing Wang in a paper on decision making in 2006. So here is the mutual inhibition setup at a resting level. No evidence is provided yet. You're sitting here at rest. There's some memory over here, but you're sitting here at a stable rest state. Suddenly a stimulus is presented. The phase plane changes because it's going into the population. So now we're in this situation of stable, stable, unstable. You started here. So you're going, blah, 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 blah. You're going to go somewhere as the evidence is accumulating. You may go here or you may go here. The noise is going to push you to one decision or the other decision. Depending upon how biased is this phase plane, you may have a higher chance of saying yes than no. So in this case, the phase plane is biased, and you go to the yes decision rather than the no decision. But decision-making models are now being developed. That is, neural network models of the circuits that are involved in decision-making in the brain. Okay, so back. Phase plane. Slow variables frozen at this level. The variables are slow. A1 and A2 are slow, the adaptation. So this phase plane is going to change. Those null-Kleins are going to move around a little bit on a slow time scale, and you're going to have to leave this state, go to that state for a while, then go back to this state. So this is that phase plane shown again. And I'm going to push a button here and have this phase plane drift slowly as the accumulating variables change. Okay, so you see you're stuck up there. There's a saddle node bifurcation. You clash with the saddle. You have to leave, go to the other, only attractor. So you're going from one attractor to the other as the phase plane slowly changes. Side point, one interesting thing about this is that we discovered in central pattern generators in here is that what your intuition would say, oh, okay, somebody's dominant, they're getting tired, they're going to release me from inhibition, and I'm going to get dominance. And then I'm going to get tired and release my partner from inhibition. That's not what's going on in this particular case. What's happening is that the partner who's suppressed is recovering, of course, from adaptation, and that partner comes up and grabs dominance. So there's multiple mechanisms of having this CPG work. It could be through an escape mechanism, or it could be through a release mechanism. And that was actually first seen experimentally in looking at a central pattern generator in a leech, using these kind of models with more, biophysical details on them, but it was essence. And it happens in this case. So we can now ask what happens if we have these two populations and we increase the strength of the percept machine in both cases. Okay? As you increase the strength of the stimulus, the experimental results, for example, in binocular rivalry, if you increase the contrast of the gratings, you increase the rate of switching. You decrease the period of dominance. So that corresponds in these models to this region right here. Increasing the strength together makes the period get shorter. You switch faster. Okay? But you look at even these simple models, and there's parameter ranges. If the inhibition is too strong, like this is the inhibition strength, if it gets too strong, there's a region in here where it no longer oscillates. Okay? It just gets stuck like this. Somebody wins and that's it. Okay? However, if you put noise on this system, you can get the system to switch. You're going to get kicked out of this domain of attraction, go into that domain of attraction. So noise can cause the switches if the dynamics don't give you the switches. So there's multiple ways of getting alternations in this system. Okay. This corresponds to what you see in experiments. This branch over here does not correspond to experiments, but this can be minimized if you put some recurrent excitation into the system. Okay, so if you add noise now, you add noise to the equations, additive noise, noise with a time scale to it, Ornstein-Uhlenbeck noise with a time scale of tau, can't read it, okay? You create noisy percept durations. High, low, and the percept duration distribution looks gamma-like, okay? So we went from this case of winner-take-all down to probability of alternations with a mean period like this, okay? All right. Okay. So conceptually, we could have an oscillator model, a limit cycle, driven with noise or additive noise and create these stochastic durations. Or we could have an attractor dynamics driven by noise. So a physicist might idealize this noise-driven alternations as a double well potential. And the noise kicks you from one well to the next well, okay? So your state is here. If you're in the minimum of a well, it's percept A. If you're in the minimum of this well, it's percept B. However, that model is not going to match the data because noisy double well potential leads you by Kramer's rate to an exponential distribution of dominance duration. This is a Poisson process. Okay, doesn't match our data. If you make the well slowly get shallower, okay, when it's occupied, then go back down slowly. When this one's occupied, you can get more gamma-like looking distributions. Okay. So here's a nice paper by Presnitzer and Hupe, short paper, you can read it, in Current Biology, comparing the qualitative, the phenomenological features of the visual bistability with the auditory bistability. And those features, for example, are the first percept is integration, and it's longer. Gamma-like distributions, predominance, durations, both auditory, visual, and plotting one percept against the previous percept duration, no or little correlation between successive percepts. So if I look at this, this would be integration, segregation, integration, segregation, okay, alternating like that. They chose their parameters so that segregation and integration were equidominant, here and here for the vision as well. Okay. So this was a short this was the very first part of the presentation. So I talked about the cocktail party problem and the time, the transient that you experience when you're going through the segregation process. So this is about that buildup of segregation. So again, it's very simple. We're using the triplets here. And you turn on the stimulus. This is a 10-second trial. When we talk about alternations, we do minutes-long trials. This is not a very exciting experiment to do as a subject. Minutes, right? Several times during the 45 minutes. But these are the curves that tell you the probability of experiencing segregation as a function of time. So the percept starts as integration. So these build-up functions start at the probability of segregation being 0. And they slowly build up over time to a steady level, which is then the probability of experiencing segregation for these different values of tone frequency difference. So the probability of segregation is going up with tone difference increase. Okay, this is 3 semitones, 6 semitones, 9 semitones. Very quickly, at high frequency difference, you go into segregation. Okay, so there's experiments, neurophysiological experiments on monkeys listening to these triplets, and we're going to get to that in a second. But I want to show you about how sometimes you use very idealized models for this kind of thing. So we did that a couple of years ago, and it's using to an extreme the notion that there's no correlation between one percept duration and the next percept duration. So a simple single trial would be integration, segregation, integration, segregation. Another trial, integration, segregation, integration, at different times. Every time you do a trial, the times of switch are going to be different. If you average over these trials, the probability of integration is going to be small or 0 at first, and you're going to build up more and more possibilities of segregation. But it's going to be a smooth function now if I average over enough trials. Okay? So we said, well, a simple model would just be, if we know that in steady state there's going to be gamma distributions, let me just make up a time course for a trial. Draw from the integrated, draw from the segregated, draw from the integrated, draw from the segregated, build up a trial, and average over them. And when you do that, you know, here's for one stream, here's for 2 streams, you can develop a nice, smooth build-up function, and you can analytically solve this problem. This is an alternating renewal process. You can analytically solve this problem. It turns out to be a coupled pair of ODEs for age-structured population. It is, the age is how long you're in this percept, okay? And you enter the other percept by integrating over anybody with this hazard function of leaving the partner percept. Okay, so this is a solvable system. This is linear. Okay. So let's take a look at the electrophysiology data. So this is, so you stick your electrode into a part of auditory cortex in the monkey, and you say, okay, what frequency do you like, neuron? And that neuron has a preferred frequency. It's tonotopically mapped from the cochlea on up into parts of auditory cortex. It says, okay, I like tone A. So we're going to choose that to be tone A, and then we'll vary the frequency of tone B. So if you simply think about, a distribution along some axis of frequency, the tonotopic axis, so to speak. Tone A, here's tone B if it's close, here's tone B if it's far away. Okay? So we're thinking in that framework. So I'm recording from tone A. Here's the response to the first triplet, A, B, A. So the response to A doesn't care what B is going to do, so you get the same response for the first tone A. Tone B, you get a different response depending upon, I'm recording at A, depending upon how far away B is along the network. Okay? So the farther away it is, the smaller is the response. This is for the first triplet. Not so different, but by the time you get to like the 10th triplet or 20th triplet, there's a big difference in how much B you see at the A location. Okay? So there's a difference in what's recorded from these triplets. So first tone, not very different. Okay? B tone at A decreases with the increasing tone frequency difference. But initially, they're pretty similar. Okay. So we're going to use these data. Michelle used these data from their from their electrophysiological data to try to fit a model for what those brain responses are to get a build-up function from the neural data and compare it to the psychophysical data. So these curves, smooth curves are the construction of a neurometric function that can be compared with the dots, which are the psychometric function from the behavioral experiment of a human. So we're comparing the monkey with the human, but trying to say what the brain might be doing here, okay? So this is recorded from the very first stage of auditory cortex. So there is a model, this is a conceptual model, put forth by somebody else who recorded responses to tone sequences called the population separation model. And I just described it with my arm. The population separation model is you've got some other tone coming down here. You record from here. It's going to be very small. So I'm going to say if the response to B is very small, it's far away, that's a good indication of segregation. They're far enough apart, it's segregation. But if they're pretty similar, that's integration. So I'm going to make some classifier and put some threshold on the spiking activity I recorded B and classify the triplets. Segregated, integrated, whatever they are. Okay? So you do that, make a neural metric function, signal classification algorithm by Michelle. If the number of B spikes is greater than ST, you say it's integrated. If the number of B spikes is less than ST, it's segregated. You've got many neurals you're recorded from, you average over neurons, you average over trials, and so on, and you, by darn, have to choose this threshold, one value of threshold, it's the same machine, different inputs, to match these data, and you can do that. You can do that. You can try to classify each triplet to what it would be like. However, you think about it a little bit and say, well, okay, so I've got these. Now let me look at the sequence of classifications I did. Okay, now let me see if I can how many integrateds did I get? How many segregateds did I get? How many integrateds? Do those sequence runs give me percept durations? Okay, they don't. They give you exponential distributions. Okay, this is like flipping a coin. with some bias to it. Integrated, segregated, integrated. So it doesn't match that. Okay? So we wanted to make, using some of these data, though, these neurophys data, to make a more neuromechanistic model. And I meant to say that Rodika Kurtu, in a talk the other day, carried on with that model of Michel's, but instead of just looking for consecutive runs, suppose I ask if I accumulate so much evidence for integration or segregation. That is, there's a threshold, and I'm just going to count evidence against the current percept I'm in to accumulate enough evidence to switch. And that gives you gamma-like distributions. So I'm not going to say any more about that. Am I doing okay? How much time do I have left? How much? 20 minutes? 10 minutes. Okay, so I think I'm going to skip this, saying that Lang and Chow did a sort of they did a sensory-based model for binocular rivalry. I had a network with a feature. I was on a feature space for binocular rivalry of this orientation or that orientation, and they could compete with one another. It was a distributed neural network model. Okay, but we're going to do this in the auditory context now. So this is going to be a sensory-based model for auditory streaming, and it's going to be an idealization of a tonotopically organized neural network. Okay, so we're going to use these neurophys data to be the inputs to our competition machine. There's very little, if any, evidence that the perceptual decision is actually made in the first stages of auditory cortex. We didn't see, well, those were short presentations, but we didn't see just by counting those segregated and integrated things that we could get perceptual representation in, we got the data that would lead into a perceptual computer. So what we're going to do is take these responses and drive a downstream network from auditory cortex at a higher level. It's going to be simple, so don't get worried. There's not going to be neurons and synapses everywhere, but it'll be simple. All right, so this is, if there's a tone, A tone presented to the A neuron, it would look like this. If the A tone is presented, so we're going to think of tonotopic axis. We're going to have a population that likes tone A, a population that likes tone B, and in between that is a population that gets input from both tones A and tones B. Okay? So if I look at the A location, A tone comes in, I get a big response, and it's got sort of a plateau like this thing here. Okay? If I look at location AB, the response is going to be less because it's only getting some of that input. It's getting spread out from lower levels. If I look at location B, I get green response to the A tone. Again, getting spread out as you fan out the response from lower levels. Okay? Those are the inputs. So here is the response to the A location for a triplet. A, B, A. Okay, here's the response in green at the B location. A, B, A. Okay, intermediate, blue, A, B, gets a good bit from both A and B, depending upon DF. Okay, so this is a model that we built with James Rankin and Elise Sussman, who does auditory psychophysics. And the experiments that I show here were done in our lab. Elise Sussman was my tutor when I learned to do auditory psychophysics. So here is the setup. We have inputs coming into the B location, inputs coming into the A location, and these are the inputs that are going to be to the population AB. So these are firing rate models. The firing rate of the A units, the firing rate of the B units, and the firing rate of the AB units, mutual inhibition. And that mutual inhibition, that coupling, is going to depend on how far apart those tones are on tonotopy. Okay? The farther apart they are, the less interaction you would expect to find. They have fast local inhibition. They have some recurrent excitation. Now we're confronting some things that are different here when we try to make a model of this auditory stimulus. The auditory stimulus is A, B, A, blank. A, B, A, blank. Okay? So it is not constant in time like in the visual case. So we have to take into account the fact that after a triplet, there's a silence. Why doesn't the system just go back to rest and we start over on every triplet? We'd be classifying every triplet. Okay, we want to extend one triplet to the next, so we get a nice percept out of it. Okay, so we have included in this recurrent excitation a time scale to remember that we have had something. So this is a slow time scale recurrent excitation. There are such recurrent excitatory network synapses in the brain, and so-called NMDA synapses. Okay, so we start the simulation off. The integrated unit is dominant. Okay, A and B units are suppressed. There's a switch. Okay, the AB unit is suppressed, and either both A and B are active, or just one of them is active. But in any case, the integrated unit, which is our marker for integration or not integration, is suppressed. There's another switch, and so on. So this basic framework can account for the alternations on the time scale of seconds by choosing the adaptation time scale and the recurrent excitation time scale in appropriate ways. Okay? So we have these experimental data, okay, as a function of tone frequency difference. For high tone frequency difference, segregation is dominant. There's a much larger fraction of time segregated than integrated. For low frequency difference, it's more dominated by integration than segregation. Okay? The normalization here is at equidominance, about 5 semitones. Okay? This is a pretty good fit for the psychophysical data with the model data for such a simple model. And it's interesting that in the process of fitting this model so well, which James did extremely well, it turned out that you could satisfy the system if the inhibition was much broader spread. Okay, not so local, but broader spread, almost like a winner-take-all setup, which is not inconsistent with activity at higher levels beyond primary auditory cortex. Coupling is more local at lower levels of sensory cortex. Out of this picture here of high period for segregation, high period for integration, if you plot the switching rate as a function of the percent segregation, you get this reverse quadratic, this parabola. It says that the maximum switching rate is around the 50-50 point. The point where you have the most uncertainty is where you switch the fastest. It's sort of a perceptual exploration statement. Okay, so we've gone on now to study the effects of perturbations of the nice continuous triplet presentation. For example, you give a few triplets and you have a pause, and then you start again with a new triplet. And that we have experiments on, and the model fits that very well. If there's a pause, okay, like here, okay, it's like starting over. If the pause is a little bit longer, then that very fast adaptation, this is a very fast adaptation here. I should have said that. This is a very fast adaptation in the neural data, much faster than the seconds of switching. Okay? So this is not determining the switch time scale. This is early adaptation, fast, but it does bias the system toward integration first. So out of this model, accounting for those valuable neurophysiological data emerges the fact that integration is first. In all the previous models, like those percept-based models, one had to build that in with initial conditions. Okay? It pops out here. Okay, so the model data and the experimental data can be matched with the model as is. We've also gone on to check experiments checking the effect of a distractor. Say between two triplets, stick in another tone. Or replace one of the tones in a triplet with a different tone. So a distractor or a deviant. Interestingly, those perturbations, different than a gap, do not cause resetting to integration. You don't start over, but you promote segregation to that. So to match those data in the model, we found that it was essential to prevent input from getting to the integrated unit. When you perturbed a triplet or you stuck in a distractor, we said ignore that. Don't give any feed to the integrator. The integrator is looking for triplets, and we've got a deviant now, and that satisfies us. So we're into a situation of now having a gating mechanism, coming up with a gating mechanism to do that. So I'm not going to go any farther into that today. So future things to do, I've talked about these gray things, but having a distributed model, not this lumped model, with continuous feature space, and having percepts be emergent, not building them in by having a percept-based system. We haven't studied yet a dynamic environment where the cues are changing with time. How do you keep track of your percepts as the cues are changing over time? And, well, the perturbation suggests that we're probably making some short-term predictions. There's probably some predictive coding going on here. And if there's a novelty that appears, you do something a little different. So those things we'll be looking at later. How do we, in terms of predictive coding, how do we learn a sequence? How do we store a sequence? For me, I think it's particularly compelling about music. If you hear a short piece of music, 10, 15 seconds, you've immediately got the rhythm. You've learned the rhythm very fast. It's repeat, 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 repeat. You can learn that very quickly. How do we do that in a neural system efficiently? How do we store all of those pieces of music that we have in our brains as limit cycles, as what? I don't know, but interesting to think about. And effects of attention. I didn't get to talk about that, but I'm going to stop now, and thank you very much.
Okay, well, thank you for a beautiful talk. I think we're allowed to have a few minutes for questions, and the microphones will come racing up to you. Are there any questions? Yeah.
Can you imagine systems where you have more numbers of steady states, multi-stable systems, and could they act then to map different percepts?
Well, we've made percept-based models of multi-stability. For example, that drifting gradient that had 3 states in it, we could account for the experimental data with a 3-attractor model. And then you ask, well, how are they coupled and so on. So we went through that exercise. But it would be interesting to do it with a sensory-based model, right? And you have to have different patterns that come up. Not done that yet. Yeah.
If you look at the switching images, then memory plays a role. If you exactly, you cannot get the same with the same freedom. If you have seen that, you always mostly lock in one of them. Is there an explanation?
You mostly lock in on one of them. You mean in this, like in this grading thing you're thinking of?
I remember some of the switchings.
Yeah.
Then, if you haven't seen it before, it changes.
Oh.
But then, if you have seen it for some time, then you are no longer so free because
I see.
you are locking in.
Yeah. Well, the theorem, the psychophysics theorem, says that you can't avoid switching. It's inevitable. You will switch. They have done experiments where they ask the subject, try to hold one percept or the other percept, and you can bias the percent of time you go from one to the other. And it's interesting. It's one of the things we've learned is it's very selective about how you present the instruction to the subject. Because one group may get one thing under an attention prescription, and another group might get something different. So it's a thing about perceptual experiments.
Am I allowed to ask a question?
Yes. Yes, you were.
So I was wondering if there are implications for things like, computer vision or Google identifying images, or even, when you talk to your phone and ask it, trying to work out language and so on.
That's
There are
interesting.
all these kinds of ideas.
Yeah, I hadn't thought about the machine. The machines, their algorithms are probably pretty darn good. I mean, they look at a lot of features, right? We're looking at very simple things here. So if you give it enough features, you can probably distinguish better. That's a good question. I don't know, yeah.
Okay, are there any other questions?
Are there any known disabilities that involve an impact on this kind of system?
Not to my knowledge, but if one could ask questions like that and use it as sort of a semi-diagnostic, I suppose. There have been experiments with meditators. If you do an experiment with a meditator, or the one I've seen, is if you meditate before you go into the booth, that your percept durations are much longer than if you don't meditate. So there are brain state things that come to play here. And one subject may differ from one day to the next, depending upon who knows what, right? What they did the night before, or did they get enough sleep, or whatever. And you do see, interestingly, some switchers are very fast, and they're almost impulsive-like. Okay, their distributions of dominance durations for one person to the other are very little different in some cases, but very rapid. So there are, differences. That maybe there's enough in some particular kind of stimuli that you could use to advantage.
We can take at least one more other question while we're changing over. Okay, well, thank you again, John. That was a beautiful talk.